Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks section 13.2 titled Graph Representations. Now part of this section you've actually kind of seen before with directed graphs back in the chapter on relations and functions. And that's the matrix representation, the adjacency matrix. Right. So hopefully that part of this section won't be so hard. Right. I don't think any part of this section really is that difficult. Right. So below are drawings of two graphs. Right. Two undirected graphs, right? No arrows, just edges between vertices. And it's simple, right? There's no self loop. There aren't any parallel edges. Right? These are simple undirected graphs. Now if you look closely, right, they look different, sure. This has like a little cross and this one doesn't. The two graphs look different, but that is only because they are drawn differently. See, this second graph here is basically this first graph, but they just kind of twist A and B around. So these are actually the same graph. The two graphs are actually the same graph because they have the same vertex set and the same edge set. Right? Both of these graphs have this vertex set and this edge set. And if two graphs have, the same vertex set and the same edge set, then they are the same graph, no matter what they look like when you compare them side by side. So that's the first lesson here, right? Just because two graphs may look different doesn't mean that they're different graphs. You have to really focus and really look at their vertex sets and their edge sets. All right, so I'll just do one of these examples on a piece of paper. Okay, now this one's actually a pretty simple example. I'm hoping you can see that this graph here, if I just rotated it, it would be exactly this graph. Alright, they didn't try to mess with labelings and make lines cross and stuff like that like in their first example. But maybe you can see that these are indeed the same graph. But let's take a look. Alright, so I'll call this V1. Alright, so let's say the vertex set for graph 1 is you have the vertices A, B, C, D, and E. And that is equal to the vertex set for graph 2. I'll call this graph 2. The vertex set for graph 2 is also, vertices A, B, C, D, and E. Wonderful. But on top of that, we have to show that they have the same edge set as well. Alright, so the edge set for graph 1. Well, you got an edge from A to B, then B to C. You also have an edge from B to D, C to D, and D to E. And I guess I should have thrown in A to E first, right? A to E as well. But there are, 6 edges here, 6 edges. And let me just go through this one here. There's A to B, there's A to B. B to C, B to C. C to D, C to D, B to D, B to D, D to E, D to E, and E to A or A to E there. And I've counted for every edge over there, and all the edges over there are also in this set, so I'm going to say this is equal to E2 as well. So check the vertex sets are the same, check the edge sets are the same. So these are the same graph, even though they look different. Again, one's just kind of rotated to look like the other. So these are indeed the same graph. All right. Then I'll let you take a look at now these graphs. See, they look exactly the same, don't they? But the labelings are different. So you're going to see here that see how there's an edge from A to C here. but there's not an edge between A and C over here, these are actually different graphs because they have a different edge set. Okay. A drawing is a convenient way to represent a small graph for a person to visualize. However, drawings can be deceptive in that identical graphs can be made to look very different if they're drawn in different ways, right? Like these two. They're identical graphs, but they look pretty different. If a graph is part of the input to a computer program, a more formal specification of a graph is required. So we're going to start getting into different ways to represent a graph, without a picture. Right? One way to represent a graph unambiguously, meaning without confusion, is to list the edges. However, a list of edges in the graph is not the most convenient way to write for a program to access the information about the graph, right? And you saw I got all these curly braces all over the place. You saw me draw an edge set. It could take a while, especially if there's more than 6 edges. A typical step in an algorithm operating on a graph would be to determine whether 2 vertices are connected by an edge, or to list all the neighbors of a given vertex. Each of these steps would require scanning the entire list of edges, which would again take a while, especially with a lot of edges. So there are 2 common ways to represent graphs for use in algorithms that make the information about a graph more accessible. So the first of these representations you're going to see is called an adjacency list. All right, an adjacency list representation for graphs. So in the adjacency list representation of a graph, each vertex has a list of all its neighbors, all the other vertices it's adjacent to, that there's an edge between. So notice that since the graph is undirected, if vertex A is in B's list of neighbors, then B must also be in A's list of neighbors. Right? And they have an animation below. I'll just do an example on paper. Right? I'll just take one of these graphs here. Right? These are actually the same graph, right? So let me do this adjacency list. So let's just look at the one on the left. I mean, they're the same graph, but let's go look at the one on the left. So here's what they call, the adjacency list representation of this graph. So I list the vertices. Right? I list the vertices. So here's A, B, C, D, and E. And they put them in little boxes. I'm not going to put them in boxes, okay? And then there's these arrows. And next to it is just a list of all the vertices, and usually in some sort of order. Here I'll put it in alphabetic order. A list of all the vertices that A is adjacent to. So A is adjacent to B. And you can put a comma. Again, they're putting them in boxes. B, I'll put commas. And also E. And that's it. And then do the same thing for B. I just list all the vertices that B is adjacent to in order. B is adjacent to A. And this is what they were saying. If B is on A's adjacency list, A should be on B's adjacency list, right? Because this is undirected. B is adjacent to A. It's adjacent to C. And adjacent to D. Very simple process here. Right? Vertex C is adjacent to B and D. Vertex D is adjacent to B, C, and E. And again, you see, C is on B's list, B is on C's list, D is on C's list, so C must be on D's list, and all this stuff. And finally, vertex E is adjacent to A and D. Very, very simple stuff. Right. And something to tie this into the first section, right? Section 13.1. If you count all these up, that gives you the total degree. Remember the degree, the total degree of a graph. Well, if you just count the number of neighbors each vertex has, that's their degree. So it's 2, degree 3, degree 2, degree 3, degree 2. Add them up, you get 12. And if you remember from last section, again, section 13.1, this is just 2 times 6, and 6 is the number of edges in the graph. Remember, the total degree is double the number of edges, and you can count them, right? 1, 2, 3, 4, 5, 6. Okay, but they're not asking for that, right? I'm just pointing that out. That if you look at an adjacency list, it's now once you have an adjacency list set up, very easy to determine total degree and the degree of each vertex. All right. Now, if a graph is represented using adjacency lists, the time required to list the neighbors of a vertex V is proportional to the degree of V. All right, so the larger the degree, the longer the time it would take. So the number of vertices to be listed, in order to determine if AB is an edge, it is necessary to scan the list of A's neighbors or the list of B's neighbors. Right? Instead of looking at all the edges, right? You just look at the neighbors for one particular vertex. So in the worst case, right, the time required is proportional to the smaller of the degree of A or degree of B. So this would definitely cut down computation time, if you were asking a computer to search and determine whether or not two vertices were adjacent. If it was going down an adjacency list, it would just go to one of those vertices and look down the list instead of looking at every single edge. All right, then this other representation, right? So you have these adjacency lists, which again are very easy to make. And then you have matrix representation for graphs, and this should be pretty familiar to you. The matrix representation for a graph with n vertices is an n by n matrix whose entries are all either 0 or 1, indicating whether or not each edge is present. If the matrix is labeled M, then M sub ij, this means the entry in the row I, column j. For a matrix representation, the vertices of the graph are labeled with integers in the range from 1 to n. Entry mij in the ith row, jth column is 1 if and only if there's an edge between vertex I and vertex j. Since the graph is undirected, Mij will be the same as Mji. Right? These matrices will be symmetrical about the main diagonal. All right, so they give us an example here. I'll just go back to my paper. Now again, they're labeling them 1, 2, 3, 4, and 5 now, but I could leave it as A, B, C, D if I want. So here's the matrix representation for this same graph. So again, there are 5 vertices, so it should be a 5 by 5 matrix. And there are 5 rows, one corresponding to vertex A, vertex B, vertex C, vertex D, vertex E. Or again, they relabeled them 1, 2, 3, 4, 5. And then same for the top, the columns. One column corresponding to vertex A, vertex B, vertex C, vertex D, and vertex E. All right, so I got a 5 by 5 matrix, and this is going to be filled with 1s and 0s. 1 if there's an edge between those vertices, and 0 if there's not. So remember, these are going to be simple graphs, so there is no self loop. There is no edge from A to A. Right, so I put a 0. Then from A to B, yeah, there's an edge, so 1. And again, from B to A, same thing. This should be a symmetrical down the main diagonal. A to C, there is no edge. So again, there'd be no edge from C to A. So when you're filling out a row, you can fill out a column as well due to the symmetry. A to D, no edge. So no edge from D to A as well. A to E, there is an edge. And so there's an edge EA as well. Alright, then down row B. Now again, no self-loops in these simple graphs. So 0 on B to B. Then B to C, yes. So C to B, yes. 1. B to D, yes. So D to B, yes. B to E, no. And so EB, no. Alright, then C. No self-loops on these simple graphs again, 0 there. C to D, yes, there's an edge. So D to C, yeah. C to E, no. So EC, there's a no, a 0. D to D, no self-loops. D to E, yes, so E to D, yes. And then finally E to E, no self-loops here, right there. And there's your matrix representation of this graph. And there's a very quick and easy relationship between this matrix representation and the adjacency list. Look at this. Right? So here was the adjacency list for that same graph. Here's the matrix for that graph. So the adjacency list will just tell you where all the ones go in your matrix. So see down that first row, there should be a 1 under the B column and E column. Right? Down the B row, there should be a 1 down the A column, C column, and D column. See, A, C, D. Down the C row, there should be a 1 down the B column and D column. Down the D row, there should be a 1 down the B, C, and E column. See, B, C, and E. And then finally down the E row, there should be a 1 down the A and D columns. And then zeros everywhere else. Right, so there's a very quick and easy transfer. If you have an adjacency list, you can easily transfer to the matrix representation for that same graph. And vice versa. Right, if you see where all the ones are, you can definitely transfer back to an adjacency list representation very quickly. All right, wonderful. All right, so they're doing that with this graph here. I'll let you watch that animation. All right, and then all they're doing, I'll leave these to you. Here's graph G with these labelings, graph H with these labelings. And they're saying which graph would have this matrix representation, which graph would have this adjacency list representation. Very, very simple, in my opinion. All right, then your challenge activity. Again, I'm going to leave these to you. This should be pretty easy. Here you're filling out, what should A be, should A be 1 or 0, should B be 1 or 0, should C be 1 or 0, and should D be 1 or 0 for this graph. Very, very simple. Level 2, you're filling in an adjacency list representation. So again, very, I think, easy. Number 3, now look, you're not given a graph, but you could draw the graph if you wanted to. You have the vertex set, and you have all the edges. And you don't really need to draw the graph, though. If you have all the edges, you know where all the ones go. Right? Remember, ones are going to go in correspondence to where the edges are. And where there are no edges, you got zeros. So again, just filling in this matrix representation. Then again, same thing here. You're given you're not given a graph. You're given a vertex set and the edge set, and asked to write this adjacency list representation. Very, very simple. And that's it. All right. So you got your additional exercises, and some of these are assigned, some might not be. I think they might all be, I don't know. Anyway, even if they aren't all assigned, I would still recommend that you look at every single problem, try to work out every single problem, get more exposure to the material, more practice. And you always have the solutions you can view if you're stuck, or if you want to check how you did, right? Again, but don't just look at them right away, right? Save the solutions till later. We'll actually work on the problems first and see how you do, and then check the solutions. Alright, so hopefully this video is a decent guide through this section. If you have any questions at all, send me a message, and I'll get back to you as soon as I possibly can. And thank you very much for watching.